Well, thank you for the opportunity to talk today. I just requested to use my own computer because I have a few of animation. So if he is ready, I can start. Yep, cool. So until recently, vast majority of people thought that mutation in GABA receptor are of loss of function variant. However, our biophysical data, as well as stratification of patients, counterintuitively show that some of them are of gain of function variant. By expressing the specific GABA receptor variant in frog oocyte, GABA-mediated current has been measured and found that both loss of function and gain of function variant in GABA receptor can cause epilepsy. You can see in this graph, in response to 100 micromolar GABA, the gain of function variant in blue causes bigger GABA-mediated current compared to control, while the loss of function variant in red causes smaller current. By using phenotype-genotype relationship, it is possible to stratify patients according to whether their variant causes loss or gain of function. For example, the patient with gain of function variant present clinically at earlier age, more commonly with focal seizure. The loss of function variant has been well studied. However, how a gain of function variant causes epilepsy is still unknown. Hence, here we created the first mouse model with a gain of function GABA-A receptor variant. We would like to first test and confirm whether we can model a gain of function GABA-A receptor DE in mice. Then we would like to see whether we can recapitulate the gain of function GABA receptor phenotype at the synaptic level, and then to test and understand the underlying disease mechanism in order to find the suitable medications for these patients. After the creation of the mouse model, the first thing we found was that GABRB3 E77K mice do not appear to have Mendelian inheritance, as only 20% of them are being born with the variant. The surviving mice also continue to die prematurely up until about P100, showing these mice definitely have some abnormal disease characteristic. We also found that these mice are significantly smaller, but gradually become to be of similar size as they grow older, which is consistent with a form of developmental delay. When we look at the overall brain activity using EEG recording, they do not show the usual spike or spike wave discharges like in other mouse models of epilepsy. However, the mutant mice, the trace in green, had dramatic increased overall EEG power spectrum, suggesting a clear differences in their brain activity compared to their wild-type littermate. As we have not yet observed spontaneous seizure in this mouse model, we tested proconvulsant challenge by injecting the PDZ at time 0 and measuring the time it took for the mice to have first tonic-clonic seizure. We found that the mutant mice in green are more susceptible to seizure compared to wild type. This suggests that they are more susceptible to seizure. We then tested different behavioral experiments. What we found the most interesting was in the locomotor test. In this open field cage, the mouse can run freely as we record. When we compare the total distance travel between the mutant mice and their wild-type littermate, we found that the mutant mice has less activity. This is complete opposite from the two published monogenic epilepsy model, N110D and D120N, with loss of function variant, which show hyperexcitability. Since these different variants are on the same gene, but produce different phenotype, it shows there is something different about the disease mechanism between them. Our hypoexcitability result is similar to the hypotonia found in the patient, which is very exciting finding for us. We then tested, we have to make sure, hold on, yep. Next, we tested whether this is a real gain of function phenotype at the cellular level. So what we did was we used slice electrophysiology and record at the individual neuron. As GABA is released from the presynaptic neuron, it binds to the postsynaptic receptor and causing the channel to open and allow the passage of chloride ion through them. The ionic passages, how much and how frequent, we can record postsynaptically by patching into the postsynaptic neuron. Here, we recorded from the cortical layer 2-3 interneuron, and these are the raw traces. The gray trace from wild-type mouse and the green from the E77K mouse. The downward hairy blips you see are the GABA-mediated chloride current. Just at a glance, you can see that the mutant mice in green has bigger event compared to the wild type. When we overlay the average traces, you can see that the average amplitude as well as area under the curve of the recorded GABA-mediated IPSC are significantly higher in mutant mice, confirming the gain-of-function mutation of GABA receptor in these mice. This is very exciting finding for us, as we now recapitulate the gain-of-function biophysical data from frog oocyte and prove that GABA receptor here in E77K mice also show gain-of-function characteristic at the synaptic level. However, this does not tell us yet how a gain-of-function characteristic lead to increased network excitability. So our collaborator group in Denmark did a bit of network recording. In this cortical network, there is a pyramidal neuron as well as surrounding inhibitory interneuron. This is same for both wild-type and mutant E77K mouse model. Let's focus on the wild-type network first. When there is a stimulation, the pyramidal neuron receives direct excitatory input as well as indirect inhibitory input through the activated interneuron. Overall, it gets excited and fire action potential. When we stimulate again and again, more and more inhibitory interneuron got recruited, resulting in increased total inhibitory input. However, they also have inhibitory input onto each other, controlling the total number of them being activated. So when they receive multiple stimulation and many of them are being recruited, instead of all of them becoming activated like this and causing superinhibition, some of them inhibit each other, resulting in controlled but increased final inhibition. Under normal circumstances, using normal GABA receptor, the final firing will still decrease, resulting in less action potential firing. You can see here, in controlled condition, there are multiple action potential firing. However, after multiple stimulation, the number of action potential firing decreases with only one action potential firing in this example. When they compare multiple neurons, the probability of action potential firing decreases, as shown there. In our E77K network, things are a little bit different. I have previously shown in IPSC data that GABA receptor on layer 2-3 interneuron are of gain-of-function phenotype. Hence, the feed-forward inhibition of interneuron on each other is stronger in E77K network. So when there is multiple stimulation and several interneurons are recruited, there would be stronger inhibition on each other, resulting in less interneuron being activated to put final inhibitory input onto the pyramidal neuron. This will in turn result in more excitability of the pyramidal neuron and increased action potential firing. This is also what they found in the recording. Compared to the control condition, after multiple stimulation, the probability of action potential firing increases. To summarize, the feed-forward network recruitment in wild-type mice lead to less probability of action potential firing, while in mutant mice, it counterintuitively causes increased action potential firing and increased network excitability. From these data, it can be suggested that disinhibition of cortical interneuron might be the underlying mechanism of increased network excitability in gain-of-function GABA receptor variant. Hence, we can now conclude that this mouse model recapitulated some of the disease phenotype, including changes in mobility, as well as gain-of-function characteristic at the synaptic level. We can also suggest that disinhibition of cortical excitability network might play as the underlying mechanism of this increased network excitability. Here, we have developed a novel mouse model of gain-of-function, which is different from loss of function, which we can use to test the underlying mechanism, as well as test the treatment options. I would like to end this talk by showing a peek into our next step. As I shown before, our beta-3 mouse has hypoexcitability characteristic on locomotor tests. When we use compound X, which is alpha-1 selective GABA-A receptor negative allosteric modulator, you can see that the increase in locomotion of mutant mice has become similar to the wild-type control, suggesting that this compound might help in the disease model. This is just a preliminary data, and we are looking forward to study further into this. I would like to thank my supervisor, Chris Reed, and our collaborator group in University of Sydney and University of Southern Denmark. Above all, I would like to thank the grant, Lundbeck Foundation, and NHMRC grant, and thank you very much for the opportunity to talk today. Thank you.
Actually, we do have time for questions there, so just a couple. Yeah, so any questions?
Really nice talk. So for this beta-3 E77K, it's heterozygous or homozygous?
This is heterozygous.
What about the homozygous?
We do not have a lot.
It took 2.5 years to make the heterozygous mice because they died.
Oh, yes. You can see, like, I'm not sure I can reconnect it, but our Mendelian ratio, can I connect it again? So our Mendelian ratios show that only 20% of them are being born with the variant. And also, they dropped dead, like, within the first month. Like, let's go back. So here. So you can see in there, only 20% are born with the E77K variant. And you can see at the weaning age, so weaning age in mouse mean the mouse does not get breastfed by the mother and the care of the mother anymore, and they have to start eating by themselves and try to survive. So at that age, you can see that most of them died very quickly. And then, yeah. So this is one of the most difficult mouse model for us to breed because first of all, when we get most of them wild type, so very little mouse, and then the mouse are dying. Yeah, so homozygous, I don't think will survive at all.
So for homozygous, are they embryonic lethal?
Most probably, yes. We also look at the embryonic data, so we actually open at the pregnant mice, and we also found this Mendelian inheritance different in the embryonic stage already. So it might be before conception even. We cannot tell because like getting ethic for that level is a bit hard.
Okay, last question.
I'll be very quick. Yeah, so I wonder, for your breeding strategy, do you use female wild type, or do you have any breeding issue with beta-3?
So I would say we tried both, like female wild type, male wild type. We have struggled with like breeding this. So we even tried, so the thing is we use 6J background. 6J background caused a bit severe mouse model in disease characteristic. So our collaborative team used 6N background. 6N background make it like survive more. So depending on the background, it might be affected as well. But like we are trying our best to, breed them.
Yeah, we did like 3 different beta-3 mouse models. So they all have, most of them have breeding issue. So this one, yeah. Also like they eat a baby. They eat their own baby.
Sorry?
Yeah, like cannibalism.
Yeah,
yes.
Do you
see that? Yeah.
Yes. I would recommend you to try with 6N background because we also have other mouse model coming up and we have very big issue with cannibalism. And when we tried on 6N background, they actually help. And also you can do Swiss mom surrogate care. Thank you.